The second section, we've got it titled as the foundation, so the core innovations first established by the lab and extending them to new domains. And the first speaker within this area, we've got Kasia talking about AI alignment. So over to you, Kasia.
Hello, everyone. My name is Kasia, and today I will present a paper, which is an ICML paper from this year called Preference Learning for AI Alignment, a Causal Perspective. Let me start with a little bit of a background for this project. So in this project, we consider the problem of LLM alignment, which is a part of LLM training process, which ensures that the model's outputs are safe, reliable, and generally aligned with human values. The most common approach for aligning LLMs is the so-called RLHF, that is reinforcement learning from human feedback. And RLHF consists of essentially two steps: reward modeling and the subsequent LLM policy optimization. The reward models are trained based on datasets of human preferences. And such preference datasets are often collected in the following way. A user submits a prompt, and then the language model generates two candidate responses. The user then has to decide which of the two responses is better according to their own judgment. And in this specific example, there is not really a universally correct answer. The preference of a user for a certain explanation style and the level of detail will depend on their unobservable characteristics, such as the expertise level. So, for instance, for a non-technical user, the response on the right-hand side may be preferred. However, for someone who is more technical, say a mathematician, that person may prefer the response on the left. And so when looking at this setup of data collection, I realized that these user-specific factors may introduce a certain form of confounding bias. And so in order to be able to talk about those issues of confounding in the preference learning setup, I decided to look at this problem from the perspective of causality. I adopted the convention of the potential outcomes framework, in which we will denote by capital letter X the prompt, and by Y and Y prime the two candidate responses, which are observed by a user. And in this causal framework, we will let the tuple X, Y, and Y prime correspond to the treatment received by an individual labeler. So all the three components, they all together constitute one treatment assignment. And then we can introduce the notion of potential rewards, which is the hypothetical latent rewards an individual would assign to a given prompt and a pair of responses if they receive that given treatment. Analogously, we will define potential outcomes as the potential preference choices made under the assigned treatment. And so if we use the standard BTL model, which is the most common one for modeling preferences, the binary preferences in practice, if we use that model to describe the relationship between the rewards and the observed labels, then the expected potential outcome will be directly determined by the difference in the potential rewards of the two candidate responses. And in this causal framing, a key question then becomes whether the expected potential outcome is identifiable. In our paper, we adapt the standard causal assumptions to the preference learning setup, and we introduced the following three assumptions: consistency, unconfoundedness, and unconditional positivity. The assumption of consistency says that if we observe a given treatment, then the observed outcome is equal to the potential outcome under that treatment. The unconfoundedness states that the potential outcomes are independent of the assigned treatment. And finally, unconditional positivity guarantees that the assignment of prompts and responses, so the assignment of treatments, is non-deterministic. Together, these three conditions are sufficient to guarantee that the expected potential outcome is identifiable and can be estimated in a non-parametric way, which we formally show in the paper. However, those three assumptions are not sufficient to estimate potential outcomes for previously unobserved treatments, which is exactly what we ultimately care about. So to enable generalization to new prompts and new responses, we introduce a model of latent treatments. In this model, we assume that the content of prompts and responses can be effectively summarized into a set of latent factors, and those latent factors can carry meaning. So this could be things like the style, conciseness of a response, or its correctness. And then the latent treatment model requires far weaker assumptions to guarantee identifiability. And we introduce two new assumptions, which will replace one of the three previously introduced assumptions. So now we will define the assumption of latent sufficiency, which states that rewards are essentially a function of the latent factors. That is, the reward are conditionally independent of the raw text that we observe given the latent factors Z. And the second assumption is the assumption of latent positivity, which requires that all combinations of latent factors have a non-zero probability of being assigned. Given the latent treatment model that we introduced, we can now replace the positivity assumption, so assumption number 3, with the assumption of sufficiency and latent positivity. And in the paper, we also show that these 4 conditions suffice to guarantee identifiability and non-parametric estimability. Great, but what does it all mean for practitioners? The key takeaways are the following. Firstly, latent factors cannot be perfectly correlated, as otherwise the assumption of latent positivity would fail. For instance, suppose we consider just 2 factors, completeness and conciseness. Complete responses often require elaboration, making succinct yet complete responses possibly rarely observable. And secondly, there cannot be any unobserved confounders, which can become an issue if user-specific variables influence the internal utility of users. For instance, the unobserved expertise level that I talked about in the very beginning of the presentation, this expertise level of users may influence both the type of prompts that users submit and then their preference for a certain type of answers. So what if those user-specific variables do come into the play? In this paper, we focus a lot of attention on the problem of confounding. In particular, we stress that the unconfoundedness can be quite easily violated. And to formalize this, we will introduce a user-specific contextual variable, which we denote here by the capital letter C. Most current practices assume that the user-specific context only influences the rewards, which is true in cases where the prompts with their corresponding responses are randomly assigned to the labelers, as depicted on this graph. However, if prompts are not randomly assigned, but written by the individuals who then score the generated responses, users scoring the lens responses of one kind may systematically differ from users scoring responses of another kind. And this is what creates the potentially dangerous confounding effect. So to illustrate and empirically investigate the impact of confounding in the observable data on the robustness of trained reward models, we performed an experiment based on the very popular in the field HH-RLHF dataset. In this dataset, prompts X are written by 2 groups of labelers, harmlessness and helpfulness focused. both groups focus on assessing the generated responses based on different and possibly conflicting objectives, because sometimes a response may be harmless, but not very helpful, or vice versa. And as a result, the distribution of those prompts written by these two groups of users with focusing on different objectives differs. And so do the potential rewards, so that the rewards now are not only a function of the prompt and the response, but also the objective. And in our experiment, we want to control the degree of confounding to generate semi-synthetic data introducing counterfactuals, that is, hypothetical decisions of what would have happened if a labeler from the first group acted according to the objective of the second group. And also, it is worth noting that the original LHF dataset demonstrates a perfect confounding effect, so that the group assignment of labelers perfectly determines their objective. And we, to test the robustness of different models, we introduce three kinds of models. And the first one is a base model, which is the most standard approach used in reward learning for AI alignment. And essentially what this model does is that it embeds the pair of a prompt and a response with an LLM. And then this embedding is concatenated with the objective that is then passed through an NLP model, and it returns the final scalar reward. The second model type is a multi-head model. And instead of concatenating the objective, I introduced two predictive heads. So there is one for each objective, and depending on the value of the objective, the latent embedding of the prompt and response is passed to one of these predictive heads. And finally, inspired by prior works on causality, I also came up with an adversarial model, which extends the multi-head model with a third decoder, whose goal was to infer the objective C from the latent representation Z. And this introduced adversarial training objective encourages the latent encoder to discard any spurious information encoded in the prompts, while trying to retain all causally relevant features to the outcome. And this plot shows in solid lines the model performance on the inconsistent examples. So that is the examples for which the objective differs from the type of the prompt. So these are those counterfactual examples that we would not see during training if we were in the scenario of perfect confounding, where the objective perfectly determines the type of the prompt. And in our results, we observed that performance of all models significantly drops as the rate of confounding in the training data increases, which is what we would expect. And then, interestingly, the base model in blue is most heavily affected, but the multi-head model in green does a little bit better because the gap in performance between the inconsistent and consistent samples is slightly smaller. And the introduction of the additional adversarial objective, which is represented here in yellow, helps to mitigate the adverse effects of confounding even better. However, ultimately, there's only as much as can be done on the model side. So with a perfect confounding rate, which is the rate of 1.0, no architecture can disentangle the effect of prompt types and objectives on the potential rewards, and all models end up performing equally badly. So to ensure robust generalization of reward models, especially in those multi-objective regimes, we suggest several directions for future work and research. Specifically, we vouch for more active forms of preference data collection and not just learning from passively observed data. This can be executed, for instance, via collection of rationals and not only preferences to identify the causally relevant features. Then we can also think about performing targeted interventions to ensure there is a sufficient overlap in the latent space. And the last direction of research that we suggest is to focus more on controllable LLM generation to enable performing those targeted interventions. I hope you found this research interesting, and if you did, then I would encourage everyone to check out the full paper for detail. And I would also like to thank my sponsors, ED, for supporting this work. Thank you.
Now we'll be moving on to GSIM, so Generative Simulations by Sam. So the floor is yours, Sam.
Yes, it's a pleasure to be here today. Really excited. So today I'll be presenting our most recent ICML paper, GSIM, Generative Simulations with Large Language Models and Gradient-Free Calibration. This is work done joint co-first author with Max Rees-Lewontin, and then also with Antoine Baton, and obviously supervised by Lavender Sharp. So what are we doing today, and what's really generative simulations? What are we doing? The broad concept is really exciting, actually, and really it's based on the concept where we can use actually extend the capabilities of a language model to actually generate entire simulations for something that we care about, and normally something that we have some sort of data set about that we can fit in this case, a model to, and I'll go into more things like that, what that is. So what this leads us to is actually create, in this case, simulations where if we had a simulation for something like such as say COVID, we can then simulate things like ask what if questions to actually test things like policies that we may not have observed, or even actually simulate things like hospitals, which we'll go into in a minute, or in this case, specific problems within a hospital. And this is really key, actually, because if we have an accurate, realistic, grounded simulator, we can start asking questions like what if questions such as how many beds, what happened if we added more beds, say in COVID-19, or lead times, say in a supply chain, or even lockdown timing. So really key critical questions. And we really want a simulator that's intervenable and that actually generalizes beyond just the historical data that we might have present for us. And really what we want to do with this work is actually to create a method that aligns to these three goals that are plausible, empirically aligned, and that we actually match from data. And we'll see just in the next slide is how can we actually create a accurate hospital bed planning simulator under surges. So for example, what is this and what we're looking at? So particularly as we were just mentioning, we want to create accurate simulators of the world to answer these what if questions. And here we actually, and we'll present the framework just in a moment, where we can actually ask a language model to essentially generate a stochastic, non-differentiable, accurate simulator of, in this case, a hospital bed scheduler for, say, certain diseases. And then if we have data from, say, a given hospital, we can actually fit it the model to the data to actually get an accurate simulator for that hospital. And then given this accurate simulator, we can then actually start asking questions. For example, what would the hospital simulation bed look like if we actually had extra beds? So these are kind of intervenable questions. And or if we maybe had started, in this case, COVID-19, if we started lockdown maybe at a particular day, and how this would actually affect the simulator over time as we simulate different states. And what's really key about this is our work is one of the first works to actually marry, in this case, discrete and stochastic state updates, in this case, patient flows, with, in this case, because we can model stochastic transitions, things like disease-specific arrival rates from Poisson distributions, really any distribution that can be coded in code, ICU versus standard bed allocation, or lengths of stay and daily mortality and finite capacities. And really why this matters. So we can show what we can do in healthcare and the complexity of it, and really we can handle actually non-differentiable and event-driven states which are underlying the simulator. And we'll come back to this at the end, where we actually can show we can actually get a quite accurate simulator. So going back to the core problem, why do we care about this? So these are real systems that often have fragmented or limited data sets and partial observed. And actually, maybe we actually want to create an accurate simulator for some sort of process in the world. And then we want to simulate maybe rare events or rare extremes. And really, normal standard machine learning models are really good in distribution. However, they're really brittle under out of distribution events or things where we really change them. And we'll show what we mean by this. For example, pure large language models, they can present plausible text or code if you went to your favorite language model application and you got some sort of code completion. However, actually, there's really no good way to quantitatively fit some sort of code simulator to some sort of data. And we present a really nice framework to do this in the most justified manner possible. And we'll revisit the fossil bed simulator at the end as well. So what makes this hard? So normally additive distribution, OOD interventions, change the mechanisms, not just the inputs. So actually having some sort of code representative structure allows us to actually, once we fit the parameters to the model and data that we observe, we can then actually understand which parts to modify to actually test different things like allocating new beds, or in this case, actually changing the fundamental parts of the, in this case, simulator to test what would happen if we simulated for things in the future. And actually, many domains are actually really difficult to simulate because they might be discrete, stochastic, and mainly non-differentiable. So this makes, if we have a non-differentiable simulator, how do we fit it to data that we observe? Because normally standard machine learning methods normally create a loss function and then minimize it with some sort of differentiable loss. And we'll go into how we do that. And actually, we really need editable modules plus data grounded numbers, really to trust what if. So for example, what's been done previously, we normally had data-driven world models. For example, neural network models, recurrent neural networks, transformers, neural ADs, and these are really accurate within distribution, but actually struggle to extrapolate to out of distribution. And then we also had LLMs actually coding environments, so flexible code. However, these are really limited to empirical grounding and actually struggled with stochastic handling because it's normally not differentiable. For example, hybrid digital twins, which our lab has proposed, which is quite popular these days, is powerful yet assumes actually some sort of smooth differentiable loss or physics and really struggles with discrete operations, for instance, in a supply chain. Whereas we propose a framework that actually overcomes these limitations. So how can we, what is the idea? So the idea is that an LM does propose a structure, for example, modules or couplings for domain knowledge. So we normally have some sort of input domain knowledge, and then the LM will generate a large structure of code, a code simulator, if you will. But this code simulator will actually run with discrete state updates plus stochastic internal components as well. And then the natural question is, how do we then fit this discrete stochastic simulator to data? And we actually use, in this case, with the first work, to marry simulation-based inference to LLM model generated by large language model, and then actually fit this with, in this case, likelihood or gradient-free methods. And once we do this, then we can iterate, for example, going back through and actually improving the model over time through textual feedback and refining the structure and the parameters. So let's go into a short example here. So for example, a user may come along with some sort of description of the simulator they want. They may optionally have a data set. Hopefully they do, they may not. But then the language model will actually produce a very detailed, in this case, code simulator, which will the LM will then essentially it will have discrete components, stochastic components, may have different modules, may have different state updates where something comes in and then goes out to a different state. And then normally this is differentiable and stochastic, so we can't just use our favorite machine learning essentially models, optimization frameworks to update or fit these parameters. So we have to actually choose between two gradient-free optimization methods, which in this case we propose simulation-based inference, which we'll go into what that is. And then another version is evolutionary strategies, which both can actually optimize non-differentiable loss functions. In this case, we actually optimize with simulation-based inference, and we optimize the Wasserstein distance, which is so you can think of this Earth distance between two different probability distributions. And then once we do this, we actually have an initial fitted simulator, but then we can actually improve this simulator. So in the next iteration, we can actually ask an LM to, given you kind of fit these previous models, see if we can actually update, or in this case, reflect to see what things could be updated more accurately in the simulator. And then we use an LM almost as a critic to critique things that are inaccurate with the simulator to give feedback, and then we regenerate the simulator model with that feedback incorporated, and then we fit it to the data again. And hopefully we see a reducing or more accurate fitting model over time through a number of iterations. And this is repeated normally for about 60 to 20 iterations. And we actually have two non-differentiable optimization pipelines. So as I was mentioning, simulation-based inference, which is really the future of optimizing simulators in this case. And this is the first work to marry them together because we start with a prior, we then actually have a simulated data set, and then we train a neural density estimator. But what's really nice is we actually get parameter distribution estimates for each parameter, which is really key, where such things like evolutionary strategies can normally find good local minima for parameters. However, we normally just get essentially a drag delta or a specific parameter, and rather than an entire distribution for the simulator. And what's really nice is we obviously, because it's non-differentiable optimization, we can then actually optimize things like Wasserstein distance as well, for, in this case, discrete stochastic simulators. And you can see an example of a very kind of simple simulator here, where you can see the code which is fitted, which we can go into later. And so how does this compare? So if we compared it with the existing benchmarks, for example, we tested on 3 different evaluation benchmarks. So COVID-19 in this case, and then a supply chain, which is commonly known as the beer game in economic theory, and then also hospital bed scheduling simulator. We can actually see that in our case, GSIM matches the ground truth best on test Wasserstein distance across tasks. For example, we tested it across, in this case, neural ODs, simple discovery methods like Cindy, recurrent neural networks, transformers, or even ablations of itself. And actually, this is really key because what we get, instead of just a black box opaque neural network model, we can actually get a fully interpretable code simulator, which actually has parameters to fit the data, and or can also model stochastic events internally as well. So how does this work? Well, actually, why is this relevant now? So if we look at, in this case, a hospital bed allocation scheduling problem, and particularly we're looking at a hospital bed allocation within the context of COVID-19 and then doing lockdowns, we can actually kind of optimize certain, in this case, policies. So we can actually search, and in this case, we can test many different policies and just running the simulator through, and then seeing what it would be like. So we can actually say lockdown starting day or extra beds, and we can actually essentially test GSIM's best policy with the ground truth optimal, where we actually use the true simulator, which was known, and we can actually see that it actually has, the LM has proposed a very accurate model, and we've been able to actually fit this to the data. And this actually models quite a few different stochastic events, which is discrete throughout, which is quite a nice achievement. And also we can do things like, if we had a simulator, for example, we can fit COVID data, we can then model out of distribution events, such as what happens if we did different lockdown policies, which were never seen during the data. And again, we can also model quite accurately. For example, we can track delayed or reduced infection peaks across different peak intensities for populations. And also actually in the cost landscape, so we can also apply it to really discrete things, such as an entire supply chain from, in this case, this is normally commonly known as the beer game in economic theory, but it can be applied to most supply chains where you have some sort of, in this case, I think it's a manufacturer, so supply chain, shipping warehouses, and then the consumer at the far end, which is an inherently discrete, in this case, stochastic system. We can also model this as well from data and also with our framework. In this case, we can actually model, once we have a simulator which is fit to real data, we can then model, say, lead time or extra capacity, and actually model, when we vary these things, what the optimal, in this case, policy would be with such an accurate simulator. And we can actually, in this case, mirror global structure of the ground truth trade-offs. So why is this really foundational today? So we're really the first to unify large language model structural search plus gradient-free calibration and plus in-the-loop textual refinement for intervenable simulations. And actually this works with discrete stochastic non-differentiable modules and supports poly optimization, and this produces interpretable modular code, which you can edit and you can trust. So the paper and code is here, and yeah, I really hope this is very useful for many people.
The final talk for this foundation section, we've got Harry talking about digital twins. And so the floor is yours, Harry.
Hopefully you can all see that. So yeah, this is a presentation about my recent paper at ICML working with my lab mate Nicholas and Mihaela as supervisor, which was called Continuously Updating Digital Twins Using Large Language Models. So before we dive in, let's try and define what a digital twin is, which is very related to the concept that Sam was just talking about in general of simulation and simulators. So a digital twin is typically referred to when we just talk about a simulator of a particular individual real-world system, which is quite an abstract definition, but we can ground that, say, as a medical patient, as our real-world system. And the goal of a digital twin is to simulate the temporal dynamics of this system over some time horizon and in response to actions and interventions from some external source. Publications on digital twins are rapidly growing at the moment. It's a very hot topic, and this is across a variety of sectors and applications. As you can see in these graphs, the publications are sort of skyrocketing, and they can be applied in domains such as healthcare, manufacturing, smart cities, engineering, and so on. We focus, of course, on healthcare applications here, and the most concrete and I guess immediate examples are for the use cases of a digital twin would be to construct a virtual twin of a patient, for example, which could be used for a number of different applications, such as where any application where simulating different scenarios could be of use. So things such as using a digital twin for a clinician to deliberate over different treatment options and guide treatment selection is a typical use case, as well as use cases in clinical trials where we may want to make clinical trials more efficient and reduce the size of control arms by, say, digitally twinning patients in treatment arms before they are given the treatment under examination, so that we can predict their responses to some control drug, which we may have ample data to be able to model the dynamics of, essentially creating synthetic control arms with digital twins of the treated patients, such that we can estimate treatment effects and things of that nature. But there are many more applications as well. So something that's often implicit or underexplored in current digital twinning literature is the fact that to build a simulator of a system, we have to define the variables that are of note or of interest. And generally, this will not be every single variable that could possibly describe the system. There has to be some level of abstraction where we're choosing some subset of variables that can describe a system and relevant actions to that system. And this is not an easy or obvious choice of how to abstract these systems. And indeed, this choice of what variables to model can change over time, particularly for complex systems and complex environments such as medicine. So an example of when the variables describing a system may change in medicine is when a novel treatment may be approved for use by some regulatory body, which then we would want to allow a digital twin of a patient to be able to simulate responses to this novel treatment. And this is essentially a new variable that has become relevant, suddenly relevant to this system that we are trying to model. And apart from new variables, there can also be new information that becomes available that should affect the way that we model the dynamics of a system. So essentially, we are basing our models off information, whether that be data or knowledge in terms of human knowledge over expected dynamics or expected treatment effects and things of that nature. And when new data is released, or new knowledge becomes available through clinical studies or anything of that nature, we would want to, that would change the environment that we're operating in. And we would want to quickly allow our model to update to this new environment. And this can be a challenge for current digital twinning techniques, because when they are designed in such a way that if variables become newly available or we want to change the variable set that we are modeling, or we want to change the data or knowledge base that we have based our model off, they can require manual redesigns or undergoing slow and potentially expensive training regimes if we're using deep learning. So in this paper, we really aimed at trying to increase and improve the adaptivity of these simulation engines so that they can more easily adapt to these changing environments, which might become more clear if we formalize a few concepts. So when we consider the construction of a digital twin, we define what we call a modeling environment that the user is operating in. And this modeling environment consists of three subcomponents, where S is the definition of the system that we are trying to model, and the abstraction that we are pursuing. And this means that we define each and every variable that we want to model the system. So each and every state variable that describes the system itself, and every action variable that can be applied to the system itself, and the transitions from one state to the next based on what action is applied. This is what we call the abstracted target system. And then there are two other components of the modeling environment, and this is essentially the information base that we should base our dynamics estimation from. And this can come from data, which may be trajectories that we have observed from the target system over time or from similar related systems. And it can also be not in the form of data, but in the form of knowledge, e.g., if we're modeling some mechanical system, there may be physical laws that we know what to expect in terms of dynamics and things of that nature. And when we want to construct these digital twins of complex real-world systems, this modeling environment can be subject to change whenever a user wants to redefine the abstraction S, or expand the information bases D or K that we are using. And we identify two capabilities that a digital twin should be able to satisfy if it can easily adapt to changes in modeling environment. And this is, it should be able to incorporate inputs and outputs of flexible dimensionality, and be able to display continuous learning capabilities. So these two capabilities naturally drove us to pursuing an LLM-based digital twin, because we see that an LLM can fulfill these desiderata. And why is this true? So LLMs operate on natural language inputs and outputs, which really decouples them from sort of rigid input-output schemas, and it allows them to operate on very flexible inputs that can change in size and dimensionality. And they also display what is called in-context learning, which is the ability to change their generation and their output distribution based on any information that is provided in their input context. So for example, the typical in-context learning example is if you want an LLM to answer some sort of question-answer pair, if you give it some examples of similar question-answer pairs in the context, in the prompt, it will perform better on the novel question-answer pair that you are prompting it on. And this is called in-context learning, and it is essentially displaying some form of continuous learning. It's able to learn from new information without having to undergo retraining or update its weights. So this is why we would like to pursue an LLM-based digital twin. However, doing this naively will lead to poor results for a few reasons. Namely, if we just sort of dump all the information that we have on a target system, and that may be a large amount of data that we've recorded of this system or of similar systems over time, or a large amount of textual knowledge into the context of an LLM, this can rapidly degrade the performance. So a naive LLM-based digital twin may not perform very well. And this can naturally encourage us to pursue some RAG-style retrieval framework where we want to retrieve only the most relevant data points to our simulation. But this can be challenging because we're considering operating mainly on time series data, which is quite out of distribution for typical encoder retrieval frameworks. So we propose our method, which we call CalmDT, which is a context adaptive language model-based digital twin, which does pursue this retrieval simulation. However, we overcome the drawbacks of pre-trained natural language encoders by fine-tuning them using a contrastive learning loss, where we construct a training database of a target system, which is split into a history and future pair, and then a number of candidate samples of related systems. And basically, we query an LLM by giving it the target history and a single candidate sample to simulate the future of the target sample. And we measure the simulation error with mean squared error in this case. And we do that across a number of candidate samples, and that allows us to rank the candidate samples by how good they are. And then using contrastive learning, we can essentially shape the embedding space of pre-trained natural language encoders so that the target trajectories are placed close in embedding space to candidate examples that improve simulation performance. And on the other hand, poor candidate samples, which lead to bad simulation performance, are moved far away in embedding space. And basically training in this manner on a data set then allows us to pursue retrieval-based simulation better than just using natural language pre-trained encoders. And once we have this fine-tuned encoder framework, we can pursue simulation via a three-step process, which is overviewed here in this block diagram. Essentially, when we want to simulate a target system, we input to the LLM a history of some number of time points and any descriptive information that we have of a system. And then we assume access to a large database of related systems. And then we use our encoders, our fine-tuned encoders, to select the top K examples from this database that are judge the best for the current history of the system. Then we go into the second step, which is called prompt formulation, where we essentially nicely lay out the information that we have, including any description of the system, all the related data sets that we've just retrieved, and the input history. And then we query the LLM to simulate the next step of the system. And then we can draw from the output distribution of the LLM in any number of ways that an LLM can be decoded. We just pursued greedy decoding here, and basically that means we sample the most likely outcome from the LLM, and then we append that to the history, and then we can do this iteratively, feeding in this new history with the appended simulation back into the start point of this simulation framework, and we can iteratively simulate step by step here until we reach the desired time horizon of simulation. As Sam covered as well, there are, of course, many related works in simulation and digital twinning. Some of them are covered here, but essentially we see that none of them fulfill our two key capabilities that we spoke about at the start of this presentation, being able to operate firstly on flexible dimensional inputs and outputs, that's D1, and being able to display some degree of continuous learning, which is D2. And we now go into some empirical comparisons of our framework with these related works. And we can see a few key takeaways. So here we can see this is simulation. This is a big table, but just look at our method, CalmDT, is down the bottom. And basically, this is in simulation of two types of medical patients. The first left two columns are cystic fibrosis patients, and the next right two columns are lung cancer patients. And we can see that in terms of the mean squared error and mean average error of our simulations, our method ranks the best on average compared to this array of related works. We also investigate the scaling properties of our method. So we see that as we increase what's called the context set size, or the number of related systems that we retrieve in our information retrieval step, the simulation error decreases, which is meaning that the system is learning from this new data that we're retrieving up to some point, and then it sort of plateaus after 5 retrieved samples in this case. And we also see that as the capabilities of the base LLM increase, its simulation performance increases as well. So we can expect better performance with better underlying LLMs. And then we have one inside experiment where we dive into the cystic fibrosis use case here, and we see how we investigate what would happen when a new treatment becomes available, inspired by an event that happened in 2012 when a treatment called ivacaftor was approved for cystic fibrosis use, and this was quite a transformational treatment. And we see, given the setting where this treatment has just been released, we assume that there is sort of limited knowledge and limited data on its effectiveness. We want to examine what changes need to be made to the prompt of the LLM, and how does this affect its simulation performance. And that's what these 3 rows here cover. Basically, we cover that as we add a short overview of a clinical trial to the context of the LLM, it improves simulation. And further, as we include a small amount of data on this new treatment, it also improves its simulation. So it is able to adapt on the fly. And yeah, that is the main takeaways from our experiments. And that's basically it.